So we follow 8 steps to use this method, or basically use this method to find the optimal solution. And as I mentioned, it only applies to problems that have 2 variables. Step 1, rewrite each constraint as an equation with one of the variables on the left-hand side. So basically, you take, you consider one variable as y, the other one as x, and you just have a simple line. Step 2, find the points 0 and y and x and 0. And then connect those two to have a straight line. That straight line is basically where that constraint is. Step 3, try the point 0, 0 for each constraint or for each line to decide if the feasible region is it's on the left side or right side of it. It's below it or above it. Also, we'll do one in an example that helps us see how these are practiced, but I'm reviewing them first. Identify the final feasible. After you do that for all the constraints, together they create their intersection creates the feasible region. And this objective function, this line that represents the objective function is called either the isoprofit or isocost. Isoprofit for maximization problems, isocost for minimization problems. Next step, determine the direction of isoprofit or isocost. Basically, you start moving it different directions to see if it increases or decreases the value of the objective function within the feasible region. After you find the correct direction of that isocost or isoprofit, then you move it in that direction. The last point that it touches before it leaves the feasible region, that will be the optimal solution. The optimal, that last point will be the optimal solution, and the value of the objective function in that point is the optimal objective function value, which we show with a z star. Okay. So let's see how these apply to an example. So let's say, so I have the eight steps over there, and then I have one simple example to solve. So we want to apply it to this problem. So step 1, rewrite each constraint as an equation, basically, and it says move one of the variables to the right side. Before even doing that, first of all, I want to start with what is it? With all the solution space, which is x and y. All right. First, I want to see where my solution space is. So that's going to be x2 and then I'll have x1. So think of x2 as y. So I'm going to turn that to an equation similar to when x2 is a function of x1. In that case, I'm going to rewrite it as x2 equals minus x1 plus 6. Does that make sense? This next one is gonna be, I use a different color. X2 equals X1 divided by 2 plus 4. Does that make sense? All right. And then we have these two sign constraints. X1 and X2 have to be positive. So basically, my feasible region is reduced to this corner, this first corner. So these are all infeasible, 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 feasible. These regions, those won't be part of the feasible region. Now, I want to see where that line is, the first one. X2 equals minus X1 plus 6. If you're not sure how to do that, if you don't know the more those techniques from calculus, you know that X1 is just like Y equals X rotated 90 degrees. But if you don't want to do that, just try these 2 points. 0 and Y, and we don't know what that is, and X and 0. So if X1 is 0, what is going to be X2 in this first constraint? First equation. If X1 is 0, X2 is 6, right? And if X2 is 0, what is X1? 6, right? So I've got 2 points, 0 and 6, 0 and 6. So that's 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6. So this is 0 and 6, and that is 6 and 0. And if you connect those, you've got the first constraint. So this was a step 2, step 2 or 3. Next step, you need to determine the direction of feasible region. Is it to the right side or the left side? And to do that, you try this point, 0 and 0. If I put 0 and 0 in that constraint number 1, does it work? Is it feasible? 0 plus 0, this one, is less than or equal to 6. So the direction is this way. So our feasible region is now reduced to a triangle, basically. And the next one, I try these 2 points, 0 and. So if X1 is 0, X2 is going to be 4. If X2 is 0, X1 is going to be, what is it going to be? Minus 8. Make sense? All right, again, those 2 points, I find those and connect them. And what I'm going to get is, so 1 point is 0 and 4. And minus 8. I can connect those 2 points. So I try the point 0 and 0, minus x1 plus 2x2 less than or equal to 8. I try 0, 0, and it seems like it's below that line, right? So now, so the feasible region is in this direction. Because of that, my feasible region is reduced. It's going to be this part. And then everything else, everywhere else is infeasible. All the points in other places are infeasible. Okay, that was step 4. Identify the final feasible region, intersection of all feasible regions, which is what we just found. And okay, next step, draw a line for the objective function. Now the objective function, if I do the same thing here, equals replace z with 0, move x1 to the left side, sorry, x2 to the left side, then you're gonna have x2 equals minus x1 divided by 3. Or, yeah. And for that, you can't do 0 and 0 because you will have only 1 point. 0 and 0, 0, 0 is 1 point. Here, let me use a different color. That's 1 point. The next point is going to be, we can try 1 and minus 3. If you put x1 equals minus 3, x2 will be 1. Then x2 is 1. And these 2 points connected, that will represent the objective function. Now we need to move this what we call isocost. Why not isoprofit? I call it isocost. That line, that green line. Why is that?
Is it because we're minimizing?
Because it's a minimization problem. Now, if I increase, if I move this line in this direction, does the objective function value decreases or increases? For example, to do that, you can see this point. Here, what is the value of objective function? It's just like, what's the intersection of this line and the feasible region? Just the point 0, 0, right? At this corner. If x1 and x2 are both 0, objective function is going to be 0. As I move this up, the value of x1 and x2 become positive. If they are positive, this value becomes more and more negative. So basically, the value of objective function is reducing. That's what we want, because it's a minimization problem. We want the objective function value to decrease. So as we move it in this direction, the value decreases more and more. What is the last point that it touches before leaving? This point, right here. So when I move it this direction, the value keeps decreasing. And the last point it touches before leaving the feasible region is that. So that point is called the optimal solution. which is what is the x and y of that point? To find the x and y of that point, basically, you write both constraints, x2, we have a system of equations. x2 minus x2 plus x1 equals 0 minus, 2x2 minus x1 equals 8. So second constraint, if you add them up, these two cancel out. 3x2 equals 14. So x2 equals 4.67, 4.67, and if you plug it into one of the constraints, x1 becomes 1.33. These are optimal, so I show them with a star. And if you plug those into the objective function, the optimal objective function value is going to be basically minus 1.33 minus 3 times 4.67, whatever that value is. That's the optimal objective function value. Okay, so that was the process. I turned every equation, every constraint to an equation with one of the variables on the left side, and then I draw the respective line, and then I tested the point 0, 0 to find the direction of feasible region. And I did that until I did it for all the constraints. The intersection of all of these constraints is going to be the feasible region. And then I draw the same, follow the same method, draw a line for the objective function. Because it was a minimization problem, I call it isocost, and I move it in the direction that decreases, because it's minimization, decreases the objective function value. And the last point that it touches before leaving the feasible region would be the optimal point. And when I plug that optimal point into the objective function, that gives me optimal OFV, optimal objective function value. Okay, so that was basically how we do it. And yeah. So next, I want you to work on this problem. So maybe follow the same method. On a piece of paper or your tablet, however you prefer.